The universe begins in absolute stillness, a silence so vast it feels like a living presence. Before any human instrument could peer across the cosmic sea, the night sky looked calm, predictable, almost obedient to the rules we had written for it. Astronomers believed they understood the rough outline of creation. A beginning defined by a violent explosion, a slow unfolding of galaxies, a steady climb toward complexity. Everything seemed to fit neatly into the cosmic timeline drawn across textbooks and simulations. But that was before a single machine, floating a million miles from Earth, dared to stare deeper than anything before it. For years, humanity had waited for the James Webb Space Telescope to awaken. Its promise was to peel back the ancient layers of time, to reveal the faint glimmer of the first stars, the first galaxies, the first sparks of creation. When it finally opened its golden eyes, the world expected beautiful images, quiet confirmations, and perhaps a few subtle surprises. What no one expected was silence filled with contradiction. The darkness was not empty. It hid structures that should not exist, light that seemed too mature for a young cosmos, and patterns that whispered of forces we thought we understood but maybe never truly did. When the first images appeared, the reaction was not celebration but confusion. Scientists stared at their screens with a mix of awe and dread, sensing that something fundamental was wrong. In the deep field, scattered like forbidden artifacts, were galaxies that looked impossibly old, spiral shapes too defined, light too bright, structures too heavy to belong to the universe's earliest chapters. These were not newborn galaxies. They looked like veterans of billions of years, yet they existed at a time when the cosmos was barely out of infancy. Something was off. Something defied the script. The farther Webb looked, the stranger the universe became. In the vast stillness, it found cosmic fingerprints that didn't match any known pattern. Colors and shapes flickered in ways no model predicted. The background glow of the early universe rippled with hints of hidden processes. The deep infrared vision of Webb, meant to be a clear window, instead behaved like a key unlocking a door no one realized was closed. Behind that door, reality twisted into forms that mocked simplicity. Astronomers who spent lifetimes piecing together the cosmic story now found their assumptions slipping like sand through their fingers. Conversations turned urgent. Theories collided. Some whispered that Webb had reached too far, too fast, exposing truths the scientific world wasn't prepared to confront. Others insisted the anomalies were illusions, misinterpretations, artifacts of a powerful instrument still learning to see. But doubt grew. The silence between each new discovery felt heavier, as if the universe itself was withholding an explanation. Every new deep-field image felt like a message from a time before understanding. Light from ancient galaxies poured in with the same quiet intensity as a confession. How could massive structures form within a few 100 million years after the Big Bang? How could the early cosmos be so mature, so organized, so impossibly bright? The universe Webb revealed looked like a painting that had already dried, even though it should have still been wet at the edges. The silence surrounding these discoveries was not peaceful, pulsed with tension. Each anomaly forced a new question. If the early universe was this complex, what happened during the first seconds, minutes, years that we never predicted? Did the laws of physics behave differently in those early moments? Were the equations we trusted missing a chapter? Or had something even more unsettling occurred? Something that rewrote the rules before we ever had the chance to witness them? Scientists gathered in conference rooms with lights dimmed, staring at enlarged images that refused to make sense. Some felt wonder, others fear. A few felt exhilaration, as though the cosmos had finally decided to reveal a deeper layer of itself. Yet beneath the excitement was a quieter, sharper feeling. The understanding that humanity had crossed an invisible boundary. We were no longer observing the universe we thought we lived in. We had stepped into a version of reality that ignored our expectations. And in that silent confrontation, a new question emerged. One that echoed across labs, observatories, and late-night discussions. What if the universe is not a single, neat timeline but something far stranger? What if we have been reading only the surface of a far more intricate design? The first observations from Webb did more than surprise scientists. They rattled the foundations of cosmology, like a soft knock on the door of our deepest assumptions. This was the moment when curiosity turned into unease. The universe, once comfortably predictable, now felt like an ancient labyrinth where every path twisted into a deeper mystery. Webb had not simply looked farther. It had exposed a truth hidden behind cosmic silence, a truth that waited patiently for billions of years, untouched, unseen, until a golden telescope drifted into its line of sight. What else lay hidden in that darkness? What realities lingered just beyond the reach of earlier eyes? The silence before discovery had shattered, replaced by a hum of questions that refused to fade. And somewhere in the vastness, as more light traveled across unimaginable distances toward Webb's mirrors, the universe seemed to whisper a warning. The deeper you look, the stranger I become. It began as an idea so ambitious that even veteran astronomers whispered about it as if it were a legend rather than a project. To build a machine capable of seeing the dawn of time meant creating a device more precise than anything humans had ever engineered. The James Webb Space Telescope was not just another observatory. It was a bet against the limits of human ingenuity, a declaration that humanity would not be confined by the darkness of deep space. Its creation was a story of fragile tools designed to uncover brutal cosmic truths, a paradox that mirrored the universe it sought to understand. Engineers and scientists did not simply build Webb. They sculpted it, piece by piece, through decades of uncertainty, failure, reinvention, and hope. Every component had to serve an impossible demand. The sunshield needed to be vast enough to block the heat of a star, yet thin enough to fold like paper. The mirrors needed to be large enough to catch faint, ancient light, yet light enough to survive the violence of launch. Every decision felt like a battle between what physics allowed and what imagination demanded. Each breakthrough pulled the telescope one step closer to existence while reminding its builders how fragile their creation truly was. On the workshop floors, the contrast was cinematic. Delicate human hands adjusting instruments designed to confront the entire cosmos. Technicians moved slowly around the golden hexagons, whispering to avoid sending vibrations through the air. Even a small slip of a screwdriver or a speck of dust could doom the mission. The silence in the clean rooms felt sacred, as though everyone present understood they were helping humanity craft its most powerful eye. The telescope's reflective surfaces, shimmering with a faint golden glow, looked almost mythic, like the shield of a hero destined for an odyssey across the universe. But behind this beauty lay constant fear. Every component Webb required was something that had never existed before. No one had built a telescope that would unfold like an origami flower in space. No one had sent a machine so far from Earth that no repair crew could ever reach it. A single failure meant the death of a dream more than 20 years in the making. Meetings often felt like cross-examinations. What if the sunshield tears? What if the mirrors misalign? What if the sensors freeze or overheat? With each question, the stakes grew heavier. Webb was not just a scientific instrument, it was a monument to human trust in the unknown. As the pieces came together, the team began to sense that they were constructing something more than hardware. They were building a time machine, one that could capture the faint glow of galaxies born when the universe was still learning to breathe. The telescope's 4 scientific instruments were crafted with almost ceremonial precision, each designed to read a different language of light. Together, they formed an orchestra waiting for cosmic music that had traveled billions of years just to reach them. The thought alone stirred a mix of awe and vulnerability. Humanity was preparing to listen to the universe in wavelengths it had never heard before. When the day of launch finally arrived, it felt less like a technological milestone and more like a myth unfolding in real time. Spectators gathered with quiet tension, knowing that a single moment could erase decades of work. As the rocket engines ignited and the ground trembled, the excitement was swallowed by fear. The roar of the engines felt like a challenge shouted into the sky. Would Webb survive the violent ascent, or would the dream vanish in a streak of fire? For minutes, people held their breath. Only when the rocket broke through the clouds did the first wave of relief wash over them, a relief fragile and temporary. The true test was still ahead. Webb traveled far beyond the reach of the International Space Station, far beyond the Moon, to a gravitational pocket known as L2. There, 1 million miles from Earth, the telescope would hang in a delicate equilibrium, balancing between the pull of the Sun and the Earth like an acrobat suspended in silence. No human had ever attempted to deploy a machine of this complexity at such a distance. Every step, every fold, every extension required perfection. Thousands of components, hundreds of motors, and dozens of hinges had to move in flawless sequence. A single mechanical hesitation could trap the instrument forever, blinding it before it could even glimpse the cosmos. For days, the world watched as commands were sent and limbs of golden machinery unfurled in slow, deliberate movements. The sun shield stretched like a silver ghost, layer by layer, until it reached the size of a tennis court. Then the mirrors shifted, opened, and aligned, their polished surfaces catching a light they were never meant to reflect, sunlight from a distant star they were tasked to avoid. Each successful deployment felt like humanity exhaling after holding its breath for an eternity. Engineers cried without shame. Scientists whispered prayers disguised as technical commentary. And when it was done, when the last bolt locked into place and the final mirror aligned, Webb floated in silence, staring at a darkness older than any memory. It had no triumphant fanfare, no dramatic music, just the quiet certainty that it was ready. Ready to look deeper than any human I had ever looked. Ready to search for the first sparks of existence. Ready to challenge everything we believed about the cosmos. Yet even then, no one could imagine how profoundly this machine would rewrite our understanding of reality. People expected clarity, data, answers. What they did not expect was the feeling that the universe itself was about to confront us. Webb was designed to reveal cosmic truth, but as it powered up and turned its gaze toward the ancient light, a different question emerged. A question whispered in control rooms and scientific journals alike. What if the truth waiting in the darkness was not what we hoped for, but something stranger, older, and far more unsettling? When Webb finally opened its golden eye to the universe, humanity stepped quietly into a new era. The machine was ready. The world was not. When the first deep-field image appeared on the monitors, the room fell into a silence so sharp it felt like gravity had tightened. For years, scientists had imagined what Webb might reveal, but what materialized looked nothing like the predictions. The image was a portrait of the early universe, except it wasn't early at all. It looked impossibly mature, like a child who had skipped infancy and leapt straight into adulthood. Galaxies that should have been faint smudges of barely formed starlight instead appeared brilliant, complex, and disturbingly old. The moment felt like witnessing a secret the universe never intended to share. The deep-field image was supposed to show the cosmic nursery, the chaotic fog where the first stars flickered to life. Instead, it showed elegant spirals, luminous cores, and structures that suggested billions of years of evolution. But the light from those galaxies had traveled from an age when the universe was only a few 100 million years old. According to every model ever written, nothing this organized should have existed at that time. Scientists leaned closer to their screens, searching for errors in processing, calibration issues, anything that could return the cosmos to its predictable script. But the data remained stubbornly clear. These galaxies were real. Across observatories and universities around the world, the reaction was the same. Disbelief followed by a creeping sense of unease. Astronomers replayed the moment the light was captured, tracing it back through time. The galaxies were too bright. Their shapes were too defined. Their mass was too large. These were not the fragile structures predicted by standard cosmology. They looked like survivors of billions of years of cosmic weathering, yet they formed in an era when the universe was still young enough to be measured in breaths. Every assumption about early cosmic growth cracked under the weight of that image. The brightness was the most puzzling feature. Young galaxies should have been dim, still gathering mass and forming stars slowly in the aftermath of the Big Bang. But Webb saw them blazing with intensity, as if lit by some unknown engine. Their luminosity suggested hyperactive star formation or immense black holes fueling fierce bursts of radiation. But those explanations strained logic. How could black holes so massive exist so early? How could stars form at such impossible speeds? The questions kept multiplying, pulling scientists deeper into a mystery that seemed to grow with every attempt to understand it. As the first image circulated through research teams, arguments erupted in quiet hallways and virtual meetings. Some scientists insisted the galaxies must be misidentified, that the distances were miscalculated. Others argued the instruments were too sensitive, detecting things that hadn't been noticed before. But hidden beneath every theory was a shared discomfort. If the galaxies were exactly what they appeared to be, then the timeline of the universe was broken. Either the cosmos evolved far faster than anyone believed, or something had fundamentally shifted our understanding of how reality unfolds. The colors in the image deepened the mystery. Webb revealed structures in rich reds and soft golds, hues shaped by wavelengths stretched across billions of years. But some of those colors indicated the presence of heavy elements, materials forged in star cycles that should not have occurred so early. Heavy elements take time, generations of stars born and dying, each adding more complexity to the cosmic mix. But here they were, in abundance, long before they should have existed. It was as if the universe had rushed through its formative years in a cosmic sprint. Scientists began constructing models, simulations, hypothetical scenarios. They worked through nights, tracing the physics backward, trying to calculate how galaxies could have condensed so rapidly. Many scenarios led to impossibilities. Matter forming faster than gravity allowed, stars emerging in clusters too dense to remain stable, black holes forming in environments contradictory to what the laws of physics permitted. Every path seemed to lead to the same conclusion, one too disturbing to accept. These galaxies should not exist. Some researchers suggested radical possibilities. Maybe the early universe was hotter than we thought. Maybe dark matter behaved differently in its youth. Maybe cosmic inflation left behind pockets of space where time flowed at different rates. The theories became daring, imaginative, almost desperate. But they all shared a tone of quiet alarm. If Webb was showing the truth, then the structure of the universe was not as steady as previously believed. It was volatile, unpredictable, capable of leaps in complexity no model had ever captured. The rooms where scientists gathered to discuss the findings felt tense, charged with the weight of a revelation no one knew how to articulate. Some felt exhilarated. This was discovery in its purest form, the universe revealing a flaw in our understanding. Others felt uneasy, sensing that the anomaly was too large, too fundamental. When an image challenges centuries of accumulated knowledge, the thrill of discovery comes with an undercurrent of fear. What else might be hidden in the deep light? What other rules might be waiting to break? Even the engineers who built Webb were stunned. They watched the data stream without the emotional armor scientists had built over years of theoretical debates. For them, this was proof the machine had succeeded beyond expectations. Yet even they sensed the unsettling implications. They had built a telescope powerful enough to peer back toward the beginning of time, but in doing so, they had allowed humanity to glimpse a version of the universe that contradicted its own history. More images followed, each one layering more confusion onto the last. There were galaxies with bizarre shapes, clumps of stars that formed too quickly, patterns of light suggesting processes that defied known physics. It felt like looking at a cosmic crime scene where the evidence pointed to impossible events. Every new discovery sharpened the suspicion that the early universe had secrets it had hidden behind billions of years of expansion. Secrets Webb had suddenly exposed. Researchers held emergency discussions, drafting papers that began with cautious phrases: unexpected structure, early formation anomaly, brightness inconsistency. But the cautious language could not conceal the truth. The universe had revealed something that didn't fit, something that shouldn't have happened, something that forced humanity to confront the possibility that the cosmic timeline, the backbone of modern cosmology, was incomplete or fundamentally flawed. As scientists studied the deepest parts of the image, a quiet realization settled over them. This wasn't a mistake. It wasn't a trick of light or a calibration error. The galaxies were real, their light undeniable, and their existence sent a message across time, a message billions of years old. The universe is not what you think it is, and the beginning of everything is far stranger than your equations ever dared to imagine. The first light Webb captured was not a gentle introduction to cosmic history. It was a challenge, a confrontation, a whisper from the past that unsettled the present. It broke open the story of creation and invited humanity to rewrite it, if we dared. Galaxies had always been the quiet storytellers of the universe, whispering secrets through their shapes, colors, and the faint glow of countless stars. Yet the galaxies Webb revealed were not quiet. They were audacious, bold, and flagrantly disobedient to the rules scientists thought governed cosmic evolution. Spiral arms curled with unexpected precision, dense clusters of stars gleamed like cities at night, and the sheer mass of some formations defied every timeline astronomers had painstakingly calculated. These were not the ragged, fledgling structures expected of a universe just a few 100 million years old. These were mature, imposing entities, seemingly in a rush to claim their place in history before the universe had even properly begun. The sheer scale of the defiance was staggering. Some galaxies contained billions of stars, their cores glowing with the intensity of energy that should have required billions of years to accumulate. According to existing models, such mass could not have coalesced so quickly. Gravity, the cosmic sculptor, would have needed eons to pull gas and dust into coherent, organized systems. Yet there they were, galaxies perfectly formed, spiraling, shimmering, and staring back across space and time. The more scientists looked, the more the universe appeared to have rewritten its own instructions, challenging humanity to question whether the laws of physics were universal or flexible depending on the epoch. It was not just size and shape that startled researchers. It was behavior. Observations indicated that these early galaxies were forming stars at unprecedented rates, lighting up their surroundings like blazing beacons. The intensity of star formation suggested processes more violent, more efficient, more rapid than any simulation had ever predicted. Some galaxies appeared to have exhausted much of their gas in the blink of a cosmic eye, leaving behind brilliant, structured remnants that resembled fully grown cosmic cities. The contrast between expectation and observation was almost cruel in its clarity. The universe was both familiar and alien, orderly and chaotic, serene and turbulent all at once. The images Webb provided forced a confrontation between two timelines, the theoretical and the observed. In one timeline, galaxies were supposed to crawl slowly through infancy, gradually gathering mass, forming stars at measured intervals, and coalescing into recognizable structures only after billions of years. In the other timeline, the one Webb revealed, the galaxies had already sprinted through those stages, emerging fully formed in a universe that should have still been learning its own rules. The collision of these timelines generated both excitement and terror among astronomers. It was as though the universe were daring humanity to reconcile what was known with what was now undeniable. Dark matter, the unseen framework upon which galaxies are thought to hang, added another layer of mystery. In some cases, Webb observed galaxies whose mass distribution did not match expected dark matter halos. Some appeared too concentrated, others too diffuse, and a few displayed rotations inconsistent with gravitational predictions. If dark matter had behaved differently in the early universe, it could help explain rapid formation, but no one had anticipated such anomalies at these scales. Each inconsistency was a puzzle piece that refused to fit into the carefully constructed image of cosmic evolution, suggesting that the invisible scaffolding of the cosmos might be more complex, more fluid, or even fundamentally misunderstood. The narrative tension deepened when Webb's instruments detected patterns in these galaxies that hinted at early black holes of extraordinary size. Supermassive black holes, millions or billions of times the mass of our Sun, should take billions of years to grow. Yet there they were, nestled in the cores of young galaxies, consuming matter at a ferocity that implied accelerated formation processes unknown to current physics. These cosmic engines lit their galaxies, shaping star formation and galactic evolution in ways that challenged not only timelines but also the fundamental understanding of gravity and matter in extreme environments. Beyond the physical anomalies, there was an emotional resonance in the observations. Each galaxy seemed to tell a story of urgency, survival, and astonishing resilience. The universe, it seemed, was not a patient, methodical artist gradually painting the cosmic canvas. It was a reckless creator, splashing light and structure across space with an energy that both inspired awe and induced existential vertigo. Astronomers found themselves grappling with the philosophical implications. If the early universe was capable of such rapid organization, what hidden principles governed its birth? Were we observing exceptions, or were we glimpsing the fundamental rule set of reality itself? Contrast framed every discovery. In one moment, the images conveyed sublime beauty. Sweeping spirals, luminous clusters, and halos of glowing gas-forming patterns that rivaled the artistry of human imagination. In the next moment, the same images carried unease. The violation of theoretical expectations, the impossibility of rapid growth, the suggestion that the universe was more cunning, more chaotic, and less predictable than previously believed. This oscillation between wonder and discomfort became the rhythm of analysis, pulling scientists deeper into a web of questions that had no immediate answers. Some researchers proposed extreme hypotheses. Perhaps the early universe experienced localized bursts of accelerated evolution. Perhaps unknown forces manipulated matter and energy on massive scales. Or perhaps our understanding of cosmic time itself needed revision. Each idea carried weighty consequences, forcing reconsideration of everything from particle physics to cosmology. Yet no matter the theory, the simple truth persisted. These galaxies existed, luminous and undeniable, and they had arrived far too early in a universe supposedly still in its infancy. The implications of these observations extended beyond science into philosophy. Humanity had always assumed that the cosmos unfolded in a predictable, almost moral sequence: birth, growth, maturity, decay. Webb suggested otherwise. The universe had no obligation to follow expectation, no loyalty to human timelines, and no need to conform to linear narratives. It had its own logic, one that was only beginning to be deciphered, and in doing so, it demanded that humanity confront the possibility that reality itself might be stranger than any model or imagination could predict. As astronomers continued to analyze the images, the contrast between the universe's apparent order and the underlying chaos became ever more pronounced. Each galaxy was a paradox. Structured yet anomalous, brilliant yet impossible, ancient yet formed in youth. Webb had not merely captured images. It had captured evidence that the rules governing the cosmos might be far more flexible, far more mysterious, and far more beautiful than previously conceived. By the end of this phase of observation, the message was clear. The early universe was not a quiet laboratory of slow development. It was a theater of astonishing creativity and defiance, a place where galaxies emerged fully formed, daring humanity to question everything we thought we knew. And the deeper Webb looked, the more it became evident that the cosmos had secrets so profound that even the most brilliant minds could only begin to grasp their magnitude. In this sense, the galaxies that broke the rules were not anomalies. They were warnings, invitations, and revelations all at once. They beckoned humanity to look further, think deeper, and accept that the universe, in its infinite complexity, had always been playing by rules far beyond our comprehension. The journey of understanding had only just begun, and the galaxies were waiting, luminous and patient, for humanity to catch up. Gravitational lensing had long been a tool in the astronomer's arsenal, a kind of cosmic trick of light that allowed scientists to peer deeper into space than otherwise possible. Yet, as Webb's data streamed in, it became clear that lensing was both a gift and a confounding challenge. The universe, it seemed, had a way of hiding truths behind spectacular illusions. Light from distant galaxies bent and twisted as it passed massive clusters, creating arcs, rings, and duplicates of the same object. The effect was mesmerizing, a visual ballet of gravity manipulating photons across billions of years. Yet it also obscured reality in ways that challenged interpretation. The first hints of a problem emerged as scientists tried to map the mass of lensing clusters. Some clusters seemed to produce distortions that suggested far more mass than could be accounted for by visible matter. Others bent light inconsistently, as if the unseen dark matter was behaving irregularly. Webb's unprecedented resolution amplified these effects, revealing details previously blurred into obscurity. Beautiful arcs traced across the cosmos were simultaneously precise tools and deceptive illusions. A galaxy might appear magnified, its brightness amplified, Yet the measurement of its distance and age could be misleading, leaving researchers in a state of cautious disbelief. The beauty of gravitational lensing was undeniable. Images captured by Webb revealed galaxies stretched into luminous ribbons, distorted circles resembling cosmic fingerprints, and overlapping patterns that made the universe seem like an intricate hologram. It was a spectacle of elegance and power, a reminder that gravity was not merely a force but an artist shaping the stage of the cosmos. Scientists described the images with poetic awe, comparing the arcs to shattered stained glass or the delicate threads of a spider's web glimmering in sunlight. Yet, amid the beauty lurked uncertainty. These visual wonders were the same phenomena that threatened to mislead the very observers who marveled at them. The challenge lay in interpretation. When light bends, it not only changes direction but also carries the fingerprints of the invisible, dark matter, cosmic expansion, and any gravitational anomalies along its path. Webb revealed galaxies appearing multiple times, mirrored across the sky, sometimes brighter in one image than another. Scientists had to untangle these echoes from reality itself. Was the galaxy seen in 3 locations actually 3 galaxies, or one entity multiplied by spacetime's curvature? Were brightness variations intrinsic to the object, or the result of gravitational amplification? Each answer demanded careful modeling, sophisticated simulations, and, often, a willingness to embrace uncertainty. As researchers delved deeper, they realized that lensing could produce illusions even more subtle and sinister. In some cases, the distortions created patterns that mimicked galaxy formation stages that did not exist. Regions of apparent density suggested star clusters that were, in truth, optical artifacts. Entire cosmic neighborhoods could be misread, leading to flawed assumptions about the early universe. Webb's clarity, ironically, was a double-edged sword. The more detail it revealed, the more room there was for misinterpretation. The cosmos had built a riddle, one in which every answer risked creating new questions. Beyond the technical difficulties, there was an emotional dimension to the lensing problem. Observers were caught between awe at the universe's artistry and anxiety over the implications of misreading its signals. A single image could evoke wonder, then doubt, then a creeping fear that humanity's understanding of cosmic history rested on shadows and illusions. Scientists spoke in hushed tones, aware that each misstep in interpretation could alter theories of galaxy formation, dark matter distribution, or even cosmic expansion. The tension in the field was palpable, as the universe both offered glimpses of truth and deliberately obscured them. Some of the most striking examples of gravitational mirages were clusters that acted as natural magnifying glasses, revealing faint galaxies from epochs that should have been invisible. These glimpses were tantalizing, potential windows into the universe's infancy, yet wrapped in layers of optical distortion. Every measurement required painstaking deconstruction, cross-referencing multiple wavelengths, simulations, and theoretical models. Even with Webb's instruments, certainty was elusive. Each lensing event became a puzzle, a delicate balance of revelation and deception, as if the universe were testing the resolve and insight of those who dared to interpret its light. Occasionally, the lensing effect revealed something even stranger. Some background galaxies appeared in configurations that did not match any known mass distribution, hinting at invisible structures or irregularities in dark matter. These anomalies sparked heated debates. Was the cosmos hiding new physics behind its optical tricks, or were the data still too early, too raw, to draw conclusions? The tension was cinematic. Each new image was a drama, an interplay of clarity and obscurity, beauty and confusion, where the laws of nature performed a complex dance that humans were only beginning to follow. Gravitational lensing also highlighted a philosophical contrast: the universe's appearance versus its reality. What was visible to the eye, even an instrument as advanced as Webb, was never guaranteed to be truthful. Light could deceive, beauty could mislead, and perceived patterns could be illusions. This duality forced scientists to develop a mindset of constant questioning, to trust their models while simultaneously doubting them, to celebrate discovery while remaining acutely aware of the universe's capacity for trickery. In this space between perception and truth, Webb's mission gained both urgency and poetic significance. to see the unseen, to interpret the ambiguous, and to confront the universe on its own enigmatic terms. As more lensing events were studied, researchers began to recognize the profound implications. Each distorted galaxy was both a gift and a warning. The cosmos had built a natural laboratory where light itself became a teacher and a trickster, offering lessons in patience, skepticism, and humility. To misinterpret a lensing effect could mean misunderstanding the history of star formation, the growth of galaxies, or even the fundamental composition of the universe. The stakes were high, but so was the reward. Through these distortions, Webb could reveal the most ancient light ever to reach human eyes, a glimpse of reality filtered through the universe's own cunning design. By the end of this chapter in exploration, a delicate truth emerged. The universe is not always what it seems. Gravitational lensing reminded humanity that perception is limited, that even the most advanced instruments can be deceived, and that beauty often hides complexity. The cosmic mirages that dazzled observers were also the keys to deeper understanding, offering both challenge and opportunity. Webb had shown that in the dance between light and gravity, mystery was not a bug of the universe. It was its very language, and to read it required patience, skill, and the courage to embrace uncertainty. The universe, in other words, was teaching humanity to look closely, to question deeply, and to accept that the line between illusion and truth is often blurred across the expanse of space and time. And as Webb continued its vigil, every new arc and ripple in the cosmos became a silent reminder that reality is rarely simple, and that the deeper one looks, the more the universe rewards those willing to unravel its enigmatic patterns. As Webb's observations piled up, it became impossible to ignore a growing unease among cosmologists. The universe, as revealed in exquisite detail, did not obey the tidy timelines that had long underpinned modern science. Time itself, it seemed, had become a question rather than a given. The earliest galaxies, the rapid formation of massive stars, the abundance of heavy elements, all pointed to a universe that had evolved far faster than theoretical models allowed. It was as if the cosmic clock was running on a schedule no one had programmed, a schedule that defied centuries of careful calculation and painstaking observation. Humanity's most fundamental assumptions about the unfolding of existence were suddenly under scrutiny. The first shock came from the realization that the light Webb captured originated from epochs when the universe was less than 1 billion years old, a fraction of its current 13.8 billion-year history. Yet the galaxies appeared fully mature, with spiral arms, dense cores, and star populations that implied long periods of growth. Scientists had expected irregular, amorphous blobs, fragile structures just beginning to coalesce. Instead, they saw intricate architecture, luminous and vast, a testament to processes that seemed impossibly accelerated. The disparity forced a confrontation with a stark possibility. Our understanding of cosmic time might be fundamentally flawed, or our models of early universe physics incomplete to the point of irrelevance. The tension was not only observational but theoretical. The expansion of the universe, driven by dark energy, is a cornerstone of cosmology. Its rate, codified in the Hubble constant, underpins distance measurements and timelines for cosmic evolution. Yet Webb's data amplified inconsistencies. Some galaxies appeared too large, too luminous, and too evolved for the time they had supposedly had to form. Even after accounting for potential lensing effects or measurement errors, the gap remained. The cosmic clock was running ahead of schedule. The further astronomers looked, the more the universe seemed to mock their calculations, forcing a philosophical reckoning. If time in the cosmos is not linear, or if it behaves differently across space, then what is the nature of reality itself? Adding to the unease was the complexity of early star formation. Webb revealed clusters with intense luminosity, indicating rapid consumption of gas and extremely efficient stellar evolution. Stars appeared to burn hotter and denser than expected, creating heavy elements at an accelerated pace. In conventional theory, multiple generations of stars are required to produce the observed chemical richness. Yet these elements appeared almost immediately, suggesting either unknown processes or a universe that had skipped steps in ways humans could barely model. Time, as a linear measure of cause and effect in stellar evolution, suddenly felt unreliable. Could the cosmos have been more inventive, more chaotic, more nonlinear than previously imagined? Physicists began exploring radical implications. Perhaps the expansion rate of the universe was not uniform, fluctuating in ways that could accelerate galactic formation. Maybe the fundamental constants of physics, considered immutable, had shifted subtly in the early universe, permitting faster accumulation of matter and energy. Some speculated that phenomena like dark energy or dark matter behaved differently in the first few 100 million years, effectively rewiring the cosmic timeline. These were not idle musings, they were forced hypotheses, necessary attempts to reconcile observation with theory. Every calculation, every simulation, became an exercise in questioning the very assumptions that had guided generations of scientists. The philosophical weight was profound. Humanity's concept of cosmic chronology was no longer a secure scaffold but a fragile construct, one that Webb's revelations had exposed as potentially illusory. The narrative that the universe unfolded in orderly stages, Big Bang, first stars, galaxy formation, cosmic maturation, was under assault. Instead of linear progression, there was the suggestion of bursts, anomalies, and uneven tempos. The universe was no longer a clockwork entity but a dynamic, perhaps capricious, system. Each new image and data point felt like peering into a story written in a language partially unknown, a story that challenged not only scientific certainty but also philosophical comfort. Even within the scientific community, reactions were mixed. Some embraced the possibility that humanity was witnessing a new chapter of physics, one that could ultimately expand knowledge and understanding. Others felt a creeping dread, the kind of existential tension that arises when familiar laws seem insufficient. The data compelled reevaluation. Were our models missing key variables? Had we misunderstood the interplay between gravity, dark matter, and baryonic matter? Or were we glimpsing something even more radical, a universe in which time itself is not a simple, measurable entity but a fluid, context-dependent phenomenon? Cosmic simulations were revisited, recalculated with new parameters, and compared against Webb's observations. Yet no configuration reproduced the maturity of these early galaxies without invoking extreme scenarios. The calculations highlighted the gulf between expectation and reality, making clear that the universe's early evolution was far stranger than conventional wisdom had predicted. Each adjustment in the models seemed to raise more questions than it answered, forcing scientists to confront the possibility that they were not merely refining knowledge. They were standing at the edge of understanding itself. The narrative web began to reveal extended beyond numerical discrepancies. The tension between theory and observation became almost personal for those who had dedicated decades to charting the universe's history. Every pixel of data felt like a whisper from the cosmos, asking whether humanity's framework for reality was sufficient. What Webb captured was more than light from distant galaxies. It was a confrontation with the very foundations of temporal perception. Were these early galaxies the product of a universe that aged faster than thought, or had humanity mismeasured the passage of cosmic time entirely? As researchers grappled with these questions, a hum of both awe and fear permeated the scientific discourse. Time, the most fundamental measure of existence, had become a variable, a question, a challenge. The cosmos no longer seemed linear or predictable. It appeared dynamic, inventive, and, at moments, indifferent to human expectations. Each new Webb observation deepened the mystery, emphasizing that the universe's story was far more complex than textbooks suggested. The past, in the light of Webb's revelations, was no longer a fixed narrative. It was an evolving puzzle, challenging observers to rethink not just the timeline of galaxies, but the very structure of reality. The broader implication was staggering. If the universe's early evolution could defy time as understood, what else might it conceal? Could there be processes occurring in the distant past that operate outside the parameters of physics as currently formulated? Could the early universe harbor mechanisms so rapid, so efficient, so strange, that humanity's conventional notions of cause and effect were inadequate? Webb had opened a window, not merely onto the cosmos, but onto the fragile boundary between knowledge and wonder, certainty and awe. In the end, the question lingered like a low hum across every observatory, every conference, every paper being drafted in secrecy. If the very flow of time in the cosmos is more complex than assumed, then what else about reality might be different than humanity has dared to imagine? And in that uncertainty, a profound mixture of fear, excitement, and curiosity settled over the scientific community, as everyone realized that looking deeper into the universe was also, unavoidably, looking deeper into the very essence of time itself. Stars are the chronometers of the cosmos, their life cycles serving as the universe's natural clock. From their formation to their death, they mark the passage of cosmic time, giving scientists a way to measure age across billions of light-years. But as Webb's telescope peeled back the layers of the early universe, it revealed stars and structures that seemed impossibly mature, defying the very chronology that had been the foundation of astrophysics. Galaxies that should have been fragile and chaotic instead gleamed with organized light, their star populations indicating ages far older than the universe itself should allow. This was the age paradox. Too old, too soon, a cosmic contradiction that shook scientists to their core. The first evidence came from the study of galactic cores. Webb revealed dense, luminous centers brimming with stars, some of which exhibited metallicities, chemical compositions indicative of multiple generations of stellar evolution. In theory, such enrichment requires billions of years of stars forming and dying, seeding the interstellar medium with heavier elements. Yet these observations came from a period only a few 100 million years after the Big Bang. The calculations did not add up. The universe was too young for stars to have lived, died, and recycled their material into subsequent generations, yet Webb's instruments showed the spectral fingerprints of just such a process. The paradox deepened when astronomers examined the distribution of stellar populations. Some early galaxies appeared to contain a mix of hot, young stars and older, cooler stars in proportions that suggested extended periods of formation and evolution. Models predicted that at this stage, most galaxies would still be dominated by nascent, hot, blue stars with little evidence of age diversity. Instead, Webb's data indicated maturity, a temporal depth that was simply not supposed to exist. Each observation forced a confrontation with uncomfortable possibilities. Either star formation occurred far more rapidly than current physics allowed, or the standard cosmological timeline was incomplete. The implications were staggering. If stars could mature this quickly, many assumptions about cosmic history needed reevaluation. The formation of heavy elements, planetary systems, and even the conditions necessary for life depended on a predictable progression of stellar evolution. A universe that produced mature stars almost immediately after the Big Bang would challenge not just astrophysics, but the entire narrative of cosmic development. Could processes in the early universe have been more violent, more efficient, or governed by unknown mechanisms that accelerated stellar growth? The questions multiplied with each new Webb observation. Some astronomers explored the possibility that these early stars formed in regions of unusually dense gas, where gravitational collapse could occur at a rate faster than models predicted. Others suggested that variations in dark matter distribution could have provided gravitational scaffolding for rapid star formation. Yet even the most aggressive scenarios struggled to match the spectral evidence. The chemical signatures and luminosity profiles indicated maturity that standard physics could not reproduce. The paradox remained stubbornly intact, a glaring contradiction in the timeline of existence. The visual evidence was equally striking. Webb's deep-field images displayed galaxies with well-defined spiral structures, populated by stellar populations that should have taken billions of years to arrange themselves. The contrast between the anticipated chaos of the early universe and the elegant order actually observed was jarring. Some spirals exhibited pronounced central bulges, a sign of advanced dynamical evolution, while surrounding disks glimmered with stars of varying ages. The imagery suggested a universe already sophisticated in structure, a cosmos that had matured at a pace that existing models could not account for. The age paradox extended to the most massive stars as well. Some early galaxies contained supergiant stars whose lifespans are measured in millions, not billions, of years. Their presence implied that not only had star formation accelerated, but it had also done so efficiently enough to produce these cosmic behemoths within an impossibly short time frame. The combination of massive stars and chemically enriched environments painted a picture of a universe that had jumped stages, skipping the slow, methodical evolution scientists had expected. The philosophical impact of the paradox was profound. Humanity's understanding of cosmic history depended on predictable stages: first light, early stars, galaxy formation, chemical enrichment. Webb's observations suggested that these stages were compressed, overlapped, or perhaps even rearranged in ways that challenged the linearity of cosmic time. Scientists were forced to consider that the universe might operate on principles far more flexible, more dynamic, and less intuitive than previously imagined. The cosmos was revealing that time, growth, and maturation were not constants but variables subject to conditions still largely unknown. In laboratories and observatories around the world, debates raged over interpretation. Were the apparent ages accurate, or could observational errors explain the discrepancy? Every possible calibration, every alternative measurement, every potential artifact was scrutinized. Yet the spectral evidence remained. The universe had aged too quickly, matured too early, and left humanity grappling with a timeline that did not make sense. The age paradox was no anomaly. It was a fundamental challenge to understanding the evolution of the cosmos. As the data continued to accumulate, scientists realized that this paradox was not confined to a few galaxies. It was widespread, a recurring pattern in the deep field observations. The implication was clear. The early universe had been more efficient, more organized, and more advanced than any theory had anticipated. Each galaxy was a silent testament to processes that had been overlooked, mechanisms that had operated with a speed and sophistication that rewrote the expectations of stellar evolution. By the end of this phase of Webb's revelations, the age paradox had shifted from a curiosity to a crisis. It demanded new physics, new models, or at the very least, a radical reevaluation of cosmic chronology. The universe, in revealing stars too old for its own age, forced humanity to confront a fundamental truth. The story of creation is not a simple narrative, and the early cosmos may be stranger, more complex, and far more mysterious than any theory has dared to suggest. Every star that glimmered in Webb's deep field images was a reminder that time, as understood by humans, may not be the unyielding constant we once believed it to be. Black holes have always been the universe's ultimate enigmas, regions of space-time so dense that nothing, not even light, can escape. They are simultaneously destructive and creative, devouring matter while shaping the formation of galaxies around them. Before Webb, supermassive black holes were thought to require billions of years to reach the titanic sizes observed in the local universe. Yet Webb's early observations painted a far more unsettling picture. Gargantuan black holes already in place when the cosmos was in its infancy, challenging the very models that governed cosmic evolution. These were not anomalies. They were evidence that the universe had accelerated processes in ways humanity had not anticipated. The first hints came from the cores of young galaxies, where intense radiation betrayed the presence of massive gravitational wells. These early supermassive black holes, millions or even billions of times the mass of our Sun, existed at a time when galaxies themselves were supposed to be barely formed. According to conventional physics, accumulating such mass would require extensive periods of steady accretion or repeated mergers, processes that simply could not operate fast enough in the first few 100 million years after the Big Bang. Yet Webb's data made it undeniable. The universe had produced cosmic monsters almost immediately after its birth, a revelation that both fascinated and terrified scientists. The implications for galaxy formation were profound. Black holes exert a gravitational influence that organizes stars, shapes spiral arms, and regulates star formation rates. Their early presence suggested that the universe had found a way to accelerate structural evolution, creating order in ways previously considered impossible. Galaxies hosting these early giants appeared more organized, with central bulges and tightly wound spirals, defying the expected chaotic, irregular shapes of primordial systems. It was as though these black holes were cosmic architects, forcing nascent galaxies into maturity at breakneck speed. Even more puzzling was the apparent interaction between these black holes and their surrounding environments. Observations revealed that some were feeding at extraordinary rates, devouring gas and dust at velocities that would have seemed impossible under standard accretion models. This extreme activity produced intense radiation, lighting up the early universe and shaping the evolution of nearby structures. The energy output was so extreme that it influenced star formation, triggered massive outflows, and altered the chemical composition of surrounding matter. The black holes were not passive anomalies. They were active agents, dramatically accelerating the evolution of the early cosmos. The challenge for physicists was to reconcile these observations with known physics. Standard models required a gradual, cumulative growth of black holes, yet Webb's data suggested rapid assembly that defied time constraints. Theoretical solutions ranged from speculative mechanisms such as direct collapse of massive gas clouds to exotic ideas involving primordial black holes formed in the earliest moments after the Big Bang. Each possibility carried immense consequences, rewriting assumptions about the interplay of gravity, matter, and energy in the infant universe. Every model tested raised new questions. What conditions allowed such rapid growth, and how common were these cosmic titans in the early epochs? The visual evidence was as dramatic as the theoretical implications. Webb's infrared instruments revealed glowing accretion disks surrounding black holes, jets of energy piercing the cosmic darkness, and gravitational interactions shaping their host galaxies with stunning precision. The imagery was cinematic, swirling clouds of matter spiraling into darkness, punctuated by bursts of light that traveled billions of years to reach Earth. For observers, it was awe-inspiring and terrifying at once. The universe was capable of creating structures of unimaginable power almost immediately after its formation. The existence of these early supermassive black holes also intensified the age paradox. If stars and galaxies could mature so quickly, and if black holes of enormous mass were already present, then the early universe was a far more dynamic, efficient, and organized environment than previously believed. It forced scientists to question the uniformity of cosmic evolution. Was this rapid development ubiquitous, or were these extreme objects rare exceptions? Webb's data suggested it might be the former, a revelation that upended the notion of gradual cosmic growth. Beyond the science, the philosophical and emotional impact was significant. Black holes, by their nature, symbolize both mystery and finality. Observing them in the early universe was like glimpsing ancient forces operating with intelligence and foresight beyond human comprehension. They were reminders of the universe's capacity to accelerate, organize, and shape reality on scales incomprehensible to the human mind. The contrast between their destructive power and their role in creation highlighted the paradoxical nature of existence itself. What devours can also build, what destroys can also organize, and what is invisible can dominate the course of cosmic history. The scientific community responded with a mix of excitement, anxiety, and reverence. Conferences, papers, and simulations multiplied, as theorists raced to incorporate Webb's revelations into a coherent framework. Some suggested new physics, others refined existing models, yet all agreed on one point. These early black holes demanded a rethinking of the universe's timeline and mechanisms. Their existence suggested that the cosmos had mechanisms of efficiency and acceleration that were previously unimaginable. By the end of this phase of observation, it became clear that black holes were more than mere curiosities. They were central actors in the drama of cosmic evolution. They exemplified the universe's ability to defy expectation, to compress billions of years of growth into mere hundreds of millions, and to challenge human assumptions about causality, time, and structure. Webb had not simply captured light from distant galaxies. It had illuminated the engines of cosmic organization, revealing forces that sculpted reality itself. In confronting these early supermassive black holes, humanity faced a profound realization. The universe was capable of accelerating its own history, of bending time and matter in ways that were both beautiful and terrifying. They were the architects of early cosmic order, the engines driving the paradox of a universe older than it should be, and the ultimate testament to the power of seeing deeper than ever before. Webb had not only opened a window to the past, it had revealed the astonishing speed, complexity, and audacity with which the universe constructs its reality. The chemical fingerprints Webb captured in early galaxies were as shocking as the images themselves. Astronomers had long assumed that the first generations of stars would produce only the simplest elements, hydrogen and helium, gradually enriching the cosmos over billions of years. But Webb revealed a universe already seasoned with heavy elements: carbon, oxygen, nitrogen, and even traces of iron, in quantities far beyond expectation. These metals are the products of multiple cycles of stellar birth and death, and their presence in the early universe implied processes far more rapid, efficient, and complex than existing models could account for. It was as if the cosmos had fast-forwarded its chemical evolution, leaving scientists scrambling to reconcile observations with theory. The implications of this unexpected chemical richness were profound. Heavy elements are essential for forming planets, creating complex molecules, and eventually supporting life. Yet Webb was showing that these elements existed at a time when galaxies were supposedly only beginning to form stars. How could the universe have generated such chemical diversity so early? Were stars forming, dying, and recycling material at breakneck speed? Were there unknown stellar processes operating in the young universe, capable of producing metals faster than anything previously considered possible? Each new spectral analysis seemed to contradict centuries of astrophysical assumptions. The distribution of these elements was equally confounding. Some galaxies exhibited concentrated metallicity in their cores, suggesting rapid enrichment in dense regions, while others displayed widespread dispersal, hinting at violent, energetic processes scattering elements across interstellar space. It was as though the early universe had developed sophisticated mechanisms for chemical engineering, dispersing the building blocks of matter in patterns previously thought impossible. These observations challenged not only our understanding of stellar life cycles but also the timeline for galactic evolution. Some theorists speculated that supermassive black holes played a role in this accelerated chemical enrichment. The energy and radiation from these black holes could trigger star formation in surrounding regions, compressing gas clouds and accelerating the production of heavy elements. Others suggested that unusual initial conditions, such as denser pockets of gas or variations in dark matter distribution, may have enabled more rapid stellar evolution. Yet, even with these hypotheses, the speed and scale of metallicity observed remained difficult to explain. The early universe appeared to be operating on a timeline that was both unfamiliar and alarming. The presence of these heavy elements also had implications for cosmology at large. Many models of the early universe rely on assumptions about the gradual enrichment of matter, predicting that early galaxies would remain chemically primitive for hundreds of millions of years. Webb's findings overturned these expectations, indicating that the universe matured chemically at an accelerated pace. The standard cosmic chronology, the carefully constructed timeline from simple to complex matter, was now in question. Humanity's understanding of how stars, galaxies, and planetary systems develop had been fundamentally challenged. The visual representation of these chemical anomalies was as dramatic as their scientific significance. Spectroscopic maps revealed galaxies with glowing regions of carbon and oxygen, their light stretching across spacetime to reach Webb's sensors. In some cases, these chemical signatures were concentrated in unexpected regions, suggesting violent interactions, rapid star formation, or previously unknown processes dispersing elements through galactic environments. The contrast between expected simplicity and observed complexity was stark, a vivid reminder that the universe had a capacity for accelerated evolution far beyond human imagination. The consequences of this rapid chemical evolution reached into the question of habitability. If heavy elements were present so early, then the raw materials for planets, moons, and perhaps even life were available far sooner than anticipated. This suggested that the universe might have been capable of supporting complexity in its earliest epochs, an idea both thrilling and unsettling. The thought that the seeds for life were sown in a universe still considered infantile challenged humanity's assumptions about cosmic chronology and our own place in the timeline of existence. Furthermore, the discovery highlighted a striking contrast between the predictability of physics on small scales and the apparent unpredictability of large-scale cosmic evolution. While laboratory experiments can reliably replicate stellar nucleosynthesis under controlled conditions, the universe had achieved similar processes in a fraction of the expected time, across vast scales, and under conditions that remain difficult to replicate in simulations. This juxtaposition emphasized the limits of human intuition when confronted with the scale and pace of cosmic phenomena. As Webb continued to catalog chemical abundances across early galaxies, a pattern began to emerge. The universe, it seemed, was not simply a slow-moving laboratory of element formation but a dynamic, high-speed workshop, producing complexity at a rate that defied traditional assumptions. Each galaxy, each spectral line, Each detection of carbon or oxygen was a message from the cosmos. Processes that humans believed required billions of years had already occurred in a fraction of that time. The speed and efficiency of these early chemical reactions raised fundamental questions about the mechanisms driving galaxy formation and the very physics of the early universe. Scientists began to frame these findings not merely as anomalies, but as evidence of a deeper truth. The early universe was capable of accelerated complexity, weaving together stars, black holes, and heavy elements in ways that contradicted conventional chronology. Webb had revealed a cosmos that matured chemically at breathtaking speed, a universe in which the seeds of planets and life may have been present far earlier than anyone dared to imagine. The chemical signatures were not just data. They were a narrative, a dramatic revelation of a universe that defies linear expectation and challenges humanity to reconsider its understanding of time, matter, and cosmic evolution. By the conclusion of this phase of exploration, it became evident that Webb's observations had unveiled a universe far richer, faster, and more intricate than previously conceived. The presence of heavy elements in such an early epoch forced a reckoning. The cosmos is capable of processes beyond our models, accelerated evolution beyond our predictions, and complexity that stretches human imagination. In that revelation lies both the awe and the unease of discovery, the recognition that the universe, in its infancy, was already mature in ways that defy comprehension. Cosmic inflation, the extraordinary expansion of the universe in its earliest moments, has long been the linchpin of cosmology, explaining the uniformity of the cosmos, the distribution of galaxies, and the seeds of structure. But Webb's observations force scientists to reconsider even this foundational concept. The galaxies Webb detected, fully formed and massive at epochs previously thought too brief for such development, implied that either inflation operated differently than theorized or that the early universe possessed unknown mechanisms to accelerate structure formation. Inflation, once a neat explanatory tool, now appeared insufficient to account for the sheer pace and sophistication of cosmic evolution revealed by the telescope. The implications of this challenge were profound. Inflation is supposed to set the initial conditions for the universe, smoothing out irregularities and creating a nearly uniform distribution of matter and energy. Yet Webb's images revealed galaxies with astonishing diversity and maturity in these early times, suggesting that the universe was capable of achieving complex organization far faster than inflationary models predicted. Could inflation have been more uneven than previously thought, creating regions of accelerated evolution? Or were there additional forces at work, pushing matter to coalesce into massive, structured galaxies almost immediately after the Big Bang? Each scenario raised profound questions about the fundamental physics that govern reality. Some theorists proposed radical extensions to inflationary theory, suggesting mechanisms such as localized bursts of accelerated expansion or variations in fundamental constants that could speed up galactic formation. Others explored the possibility that exotic phenomena, perhaps interactions between dark matter and baryonic matter, or previously unknown forms of energy, had acted in the early universe to catalyze rapid growth. While speculative, these ideas underscored a growing consensus. The early universe was far more dynamic, unpredictable, and efficient than standard models allowed. Webb's data forced cosmologists to confront uncomfortable possibilities, challenging assumptions that had stood unchallenged for decades. The telescope's high-resolution imaging revealed not only massive, mature galaxies but also striking patterns in their distribution and alignment. Some appeared in dense clusters, hinting at early formation of large-scale structure, while others were isolated, suggesting uneven, patchy evolution across the cosmos. These observations complicated the neat picture provided by inflationary theory, which predicts a mostly homogeneous, isotropic early universe with slight fluctuations that grow gradually over billions of years. Webb's findings suggested that structure could emerge much more rapidly and in more complex configurations than previously imagined, forcing a reevaluation of how the universe organizes itself on the largest scales. Moreover, the apparent efficiency of early galaxy formation highlighted a stark contrast between theoretical expectations and observational reality. According to standard cosmology, galaxies at such early epochs should have been small, fragile, and irregular, gradually merging and growing over time. Instead, Webb captured luminous, well-structured galaxies, some exhibiting spiral arms, dense cores, and extensive star populations. The universe was achieving in a few 100 million years what conventional models predicted would require billions. This tension between expectation and observation became a central puzzle, driving theorists to explore whether new physics or adjustments to inflationary models could reconcile the discrepancy. The discovery also had profound implications for understanding the formation of cosmic filaments and voids, the vast web-like structures connecting galaxies across space. Webb's images revealed early hints of these patterns, suggesting that the scaffolding of the universe may have been established far earlier than previously thought. The rapid emergence of structure implied that gravity and other fundamental forces had operated with unusual efficiency, shaping the cosmos into coherent frameworks almost immediately after the inflationary epoch. These observations challenged the notion that the universe's large-scale architecture required eons to develop, emphasizing instead the possibility of accelerated, organized growth from the very beginning. The philosophical and emotional impact of these revelations was significant. Inflation, once a comforting explanation for the uniformity and origin of the universe, now seemed incomplete. Humanity's picture of the cosmos as a predictable, orderly expansion was replaced with a vision of a universe capable of astonishing acceleration, complexity, and rapid evolution. The contrast between theoretical expectations and observational reality created a tension that was both thrilling and unsettling, forcing scientists and philosophers alike to confront the possibility that the universe's earliest moments were far stranger than imagined. Webb's findings also prompted a reassessment of the interplay between dark matter, dark energy, and visible matter in the early universe. If inflation alone could not account for the rapid formation of massive galaxies, then perhaps these unseen components played a more active role than previously understood. Could dark matter have provided gravitational scaffolding that accelerated galaxy assembly? Could dark energy have influenced the timing and pace of cosmic expansion in ways yet unmodeled? These questions underscored the interconnectedness of cosmic forces and highlighted how Webb's observations were reshaping the understanding of the universe from its very foundations. The telescope's ability to capture both the brightness and composition of these early galaxies offered additional clues. Spectroscopic data revealed heavy elements, high star formation rates, and energetic processes occurring simultaneously across vast distances. These combined factors pointed to a universe that had not only expanded rapidly but had also evolved chemically and structurally with remarkable speed. The challenge for theorists was to integrate these observations into a coherent model, one that could explain the apparent acceleration without violating fundamental principles of physics. By the end of this phase, the significance of Webb's contributions was undeniable. Inflation alone could no longer serve as a complete explanation for the universe's early evolution. The telescope had exposed the limitations of conventional models and highlighted the need for new frameworks that account for rapid structure formation, chemical maturity, and complex galactic organization. In doing so, it emphasized a profound truth. The early universe was far more dynamic, efficient, and surprising than humanity had ever anticipated, and our understanding of cosmic origins would never be the same. Webb had not merely looked back in time, it had revealed a universe operating on accelerated rhythms, a cosmos capable of achieving in hundreds of millions of years what theory suggested required billions. The images, spectra, and data collectively challenged the inflationary paradigm, inviting scientists to rethink the very mechanisms that drive the expansion, organization, and evolution of all that exists. The universe, in its infancy, had already matured in ways that defied expectation, and Webb had given humanity a front-row seat to this astonishing, unsettling, and transformative revelation. Cosmic collisions are among the most dramatic events in the universe, reshaping galaxies, igniting star formation, and sending shockwaves of energy across vast stretches of space. Before Webb, these interactions were well documented in the relatively nearby universe, but little was known about their prevalence in the first billion years after the Big Bang. The telescope's extraordinary sensitivity and resolution changed that. Webb revealed a universe teeming with interactions, with galaxies merging, twisting, and colliding at a pace that defied conventional expectations. What was previously thought to be a slow and gradual process of galactic assembly was, in the early cosmos, a frenetic ballet of forces, matter, and energy operating on scales both immense and violent. The first images showed galaxies stretched and distorted, their stellar populations flung into arcs and tidal tails as gravitational forces tore them apart and reshaped them. Some appeared to be in the earliest stages of merging, elongated and warped, while others exhibited fully intertwined cores, indicating collisions that had already progressed significantly. These observations suggested that the universe's formative years were far more chaotic than previously assumed, with mergers playing a central role in both accelerating galactic maturity and redistributing mass and energy. Each image was a striking tableau of destruction and creation intertwined, a reminder that cosmic violence is often the engine of order. Star formation in these colliding galaxies was particularly intense. Webb's instruments detected bursts of ultraviolet and infrared light, indicating regions where gas clouds were compressed and ignited into stellar nurseries. The pace of star formation exceeded what models had predicted for galaxies of this age, highlighting the catalytic role of collisions in accelerating cosmic evolution. These were not leisurely bursts of activity. They were concentrated, energetic, and efficient processes that forged stars and enriched the interstellar medium with heavy elements at an astonishing rate. The violent interactions effectively fast-forwarded galactic development, creating complex structures far earlier than theorists had anticipated. The gravitational dynamics of these mergers added another layer of mystery. Some early galaxies displayed rotations and mass distributions inconsistent with current models, suggesting that interactions in the dense early universe could lead to unexpected configurations. The combination of multiple colliding galaxies in close proximity, coupled with the influence of dark matter halos, created environments where conventional laws of formation seemed stretched, if not outright challenged. Webb's observations highlighted that the early cosmos was not a calm, uniform environment, but a seething, interconnected network of forces, pushing galaxies to evolve at breakneck speed. Beyond the physical phenomena, the visual spectacle of these collisions was breathtaking. Streams of stars arced across space like ribbons of light, glowing gas clouds formed luminous bridges between galaxies, and regions of intense radiation flared where matter was compressed to extremes. Each scene was simultaneously beautiful and terrifying, a reminder that the universe is a realm of contrasts, creation and destruction, chaos and order, elegance and violence. The imagery captured the imagination while forcing scientists to confront the limitations of their models and assumptions. Some researchers began exploring whether these collisions could account for other anomalies observed by Webb. Could rapid mergers help explain the unexpected maturity of early galaxies? Could interactions accelerate the growth of supermassive black holes by funneling gas into galactic cores? Could they redistribute heavy elements, contributing to the chemical enrichment observed far earlier than models predicted? The evidence increasingly suggested that collisions were not peripheral events but central mechanisms in the rapid evolution of the early universe. The emotional resonance of these findings was palpable within the scientific community. Observers were confronted with a cosmos simultaneously elegant and violent, predictable and chaotic. The collisions illustrated a fundamental principle. The universe builds complexity through both creation and destruction, and the early cosmos may have leveraged this principle with extraordinary efficiency. Each merger captured by Webb was a narrative of transformation, a testament to the processes that shape galaxies, stars, and ultimately the cosmic environment in which life may one day emerge. Furthermore, these observations emphasized the interplay between large-scale structure and local dynamics. Collisions did not occur in isolation. They were influenced by the surrounding cosmic web, by neighboring galaxies, and by the distribution of dark matter. This interconnectedness suggested that the early universe was a highly interactive system, where events in one region could catalyze changes in another, accelerating the overall pace of evolution. Webb's ability to resolve these interactions provided a level of detail previously unattainable, offering insight into the mechanisms by which chaos can generate order on cosmic scales. The implications of these collisions extended beyond astrophysics into philosophy and cosmology. Humanity tends to perceive order as emerging slowly, gradually, and predictably, but Webb's observations painted a different picture. The early universe was a place of intense, rapid transformation, where violent interactions drove structure, chemistry, and evolution forward at astonishing speeds. The cosmos, it seemed, did not require patience. It was capable of immediate and dramatic innovation, reshaping itself with a combination of force, gravity, and energy that stretched the imagination. By the end of this chapter in Webb's revelations, a stark reality emerged. Collisions were not mere curiosities. They were fundamental drivers of early cosmic evolution. They accelerated the formation of stars and galaxies, shaped supermassive black holes, redistributed matter and heavy elements, and contributed to the unexpected maturity observed throughout the early universe. Webb had revealed a cosmos in motion, a universe where violence and elegance coexisted, and where the interplay of forces forged complexity far more rapidly than humanity had ever imagined. In observing these galactic encounters, humanity was offered a glimpse of the universe's creative power through destruction. A dynamic, breathtaking process that challenged assumptions, inspired awe, and reframed our understanding of how the cosmos grows, evolves, and defies expectation. The early universe was not a passive backdrop but an active, turbulent theater, and Webb had captured its drama in unparalleled clarity. Cosmic collisions are among the most dramatic events in the universe, reshaping galaxies, igniting star formation, and sending shockwaves of energy across vast stretches of space. Before Webb, these interactions were well documented in the relatively nearby universe, but little was known about their prevalence in the first billion years after the Big Bang. The telescope's extraordinary sensitivity and resolution changed that. Webb revealed a universe teeming with interactions, with galaxies merging, twisting, and colliding at a pace that defied conventional expectations. What was previously thought to be a slow and gradual process of galactic assembly was, in the early cosmos, a frenetic ballet of forces, matter, and energy operating on scales both immense and violent. The first images showed galaxies stretched and distorted, their stellar populations flung into arcs and tidal tails as gravitational forces tore them apart and reshaped them. Some appeared to be in the earliest stages of merging, elongated and warped, while others exhibited fully intertwined cores, indicating collisions that had already progressed significantly. These observations suggested that the universe's formative years were far more chaotic than previously assumed, with mergers playing a central role in both accelerating galactic maturity and redistributing mass and energy. Each image was a striking tableau of destruction and creation intertwined, a reminder that cosmic violence is often the engine of order. Star formation in these colliding galaxies was particularly intense. Webb's instruments detected bursts of ultraviolet and infrared light, indicating regions where gas clouds were compressed and ignited into stellar nurseries. The pace of star formation exceeded what models had predicted for galaxies of this age, highlighting the catalytic role of collisions in accelerating cosmic evolution. These were not leisurely bursts of activity. They were concentrated, energetic, and efficient processes that forged stars and enriched the interstellar medium with heavy elements at an astonishing rate. The violent interactions effectively fast-forwarded galactic development, creating complex structures far earlier than theorists had anticipated. The gravitational dynamics of these mergers added another layer of mystery. Some early galaxies displayed rotations and mass distributions inconsistent with current models, suggesting that interactions in the dense early universe could lead to unexpected configurations. The combination of multiple colliding galaxies in close proximity, coupled with the influence of dark matter halos, created environments where conventional laws of formation seemed stretched, if not outright challenged. Webb's observations highlighted that the early cosmos was not a calm, uniform environment, but a seething, interconnected network of forces, pushing galaxies to evolve at breakneck speed. Beyond the physical phenomena, the visual spectacle of these collisions was breathtaking. Streams of stars arced across space like ribbons of light, glowing gas clouds formed luminous bridges between galaxies, and regions of intense radiation flared where matter was compressed to extremes. Each scene was simultaneously beautiful and terrifying, a reminder that the universe is a realm of contrasts, creation and destruction, chaos and order, elegance and violence. The imagery captured the imagination while forcing scientists to confront the limitations of their models and assumptions. Some researchers began exploring whether these collisions could account for other anomalies observed by Webb. Could rapid mergers help explain the unexpected maturity of early galaxies? Could interactions accelerate the growth of supermassive black holes by funneling gas into galactic cores? Could they redistribute heavy elements, contributing to the chemical enrichment observed far earlier than models predicted? The evidence increasingly suggested that collisions were not peripheral events but central mechanisms in the rapid evolution of the early universe. The emotional resonance of these findings was palpable within the scientific community. Observers were confronted with a cosmos simultaneously elegant and violent, predictable and chaotic. The collisions illustrated a fundamental principle. The universe builds complexity through both creation and destruction, and the early cosmos may have leveraged this principle with extraordinary efficiency. Each merger captured by Webb was a narrative of transformation, a testament to the processes that shape galaxies, stars, and ultimately the cosmic environment in which life may one day emerge. Furthermore, these observations emphasized the interplay between large-scale structure and local dynamics. Collisions did not occur in isolation. They were influenced by the surrounding cosmic web, by neighboring galaxies, and by the distribution of dark matter. This interconnectedness suggested that the early universe was a highly interactive system, where events in one region could catalyze changes in another, accelerating the overall pace of evolution. Webb's ability to resolve these interactions provided a level of detail previously unattainable, offering insight into the mechanisms by which chaos can generate order on cosmic scales. The implications of these collisions extended beyond astrophysics into philosophy and cosmology. Humanity tends to perceive order as emerging slowly, gradually, and predictably, but Webb's observations painted a different picture. The early universe was a place of intense, rapid transformation, where violent interactions drove structure, chemistry, and evolution forward at astonishing speeds. The cosmos, it seemed, did not require patience. It was capable of immediate and dramatic innovation, reshaping itself with a combination of force, gravity, and energy that stretched the imagination. By the end of this chapter in Webb's revelations, a stark reality emerged. Collisions were not mere curiosities. They were fundamental drivers of early cosmic evolution. They accelerated the formation of stars and galaxies, shaped supermassive black holes, redistributed matter and heavy elements, and contributed to the unexpected maturity observed throughout the early universe. Webb had revealed a cosmos in motion, a universe where violence and elegance coexisted, and where the interplay of forces forged complexity far more rapidly than humanity had ever imagined. In observing these galactic encounters, humanity was offered a glimpse of the universe's creative power through destruction. A dynamic, breathtaking process that challenged assumptions, inspired awe, and reframed our understanding of how the cosmos grows, evolves, and defies expectation. The early universe was not a passive backdrop but an active, turbulent theater, and Webb had captured its drama in unparalleled clarity. Cosmic dust, once thought to be mere detritus of star formation, emerged as one of Webb's most startling revelations. This fine particulate matter, microscopic grains of carbon, silicates, and metals, pervades galaxies, influencing light, chemistry, and the very dynamics of star formation. In the nearby universe, dust is abundant and well-studied, but Webb revealed massive quantities of dust in galaxies that existed when the universe was less than 1 billion years old. This presence so early was perplexing. According to traditional models, the first generations of stars had barely formed, insufficient to produce the heavy elements necessary to create dust in such amounts. Yet Webb's instruments detected it across multiple early galaxies, forcing scientists to confront the reality that the universe was chemically and structurally more mature than theory predicted. The presence of early cosmic dust carried profound implications for understanding star formation. Dust cools interstellar gas, allowing it to collapse under gravity to form stars more efficiently. Its early abundance suggested that star formation could proceed at rates far higher than models had anticipated, potentially explaining the rapid emergence of massive, mature galaxies. But the source of the dust itself posed a mystery. Traditional stellar evolution posits that asymptotic giant branch stars and supernovae produced dust over millions of years. The sheer volume observed in Webb's early galaxies implied either an extraordinarily efficient dust production mechanism or entirely unknown processes operating in the first few 100 million years after the Big Bang. Observationally, the dust revealed itself in striking ways. Infrared images showed galaxies glowing with warmth and luminosity, the result of starlight absorbed and re-emitted by dust grains. In some cases, dust clouds obscured central regions, hinting at dense, complex environments where stars were forming in concentrated bursts. The interplay of light and dust created visual contrasts, bright, glowing arcs punctuated by dark, opaque patches, giving the impression of cosmic chiaroscuro, where creation and concealment coexisted. For scientists and viewers alike, the imagery was both beautiful and unsettling. A universe that seemed to conceal as much as it revealed, a place where clarity and mystery existed side by side. The composition and distribution of dust further challenged theoretical models. Webb detected variations in dust density across early galaxies, with some regions astonishingly rich and others sparse. This patchiness suggested dynamic processes at play. Violent supernova explosions, galactic winds, and energetic radiation from nascent black holes could disperse dust unevenly, influencing subsequent star formation and chemical evolution. The intricate patterns revealed a cosmos that was not only active but also capable of sophisticated, almost deliberate organization on massive scales. Dust, far from being incidental, became a central player in the drama of early cosmic evolution. The implications for cosmic visibility were also profound. Dust absorbs ultraviolet and visible light, meaning that some of the earliest, most luminous regions of star formation could have been hidden from previous telescopes. Webb's infrared capabilities allowed scientists to peer through these dusty veils, uncovering galaxies and star-forming regions that had remained invisible. In this sense, cosmic dust acted both as an obstacle and a gateway, a barrier to ordinary observation but a conduit to deeper understanding when illuminated by the right technology. Humanity was witnessing the universe's hidden machinery in unprecedented detail. Beyond astrophysics, the presence of early dust introduced philosophical tensions. Dust is a product of prior generations, stars that have lived and died, seeding the cosmos with their remnants. Its abundance in the early universe suggested a history that had already been written in miniature, a story of creation and destruction compressed into an unexpectedly short time frame. The universe appeared capable of rapid cycles of birth and death, condensation and dispersion, hinting at an efficiency and foresight that bordered on the poetic. For humanity, the implications were humbling. The cosmos was more organized, more complex, and more mature at its inception than previously imagined. The interplay between dust, star formation, and galaxy evolution also suggested that early cosmic environments were far from uniform. Some galaxies exhibited dust-rich regions that accelerated star formation, while others remained relatively pristine, dominated by hot, young stars. This variation hinted at a patchwork early universe, where conditions for growth and chemical evolution were uneven yet extraordinarily effective. Webb's ability to map these differences in such detail offered unprecedented insight into the dynamics that governed the young cosmos, emphasizing that the universe was not a monotone landscape but a vibrant, evolving tapestry of structure, chemistry, and energy. The discovery of early cosmic dust further intertwined with other anomalies Webb had uncovered, including massive stars, supermassive black holes, and rapid chemical enrichment. Dust was both a consequence and a catalyst, participating in the accelerated evolution of galaxies, while also revealing their inner complexity. The feedback loops were staggering. Dust enabled star formation, stars produced heavy elements, and both contributed to the growth of galaxies at a pace that contradicted standard models. Observing these processes simultaneously provided a new lens through which to view cosmic history, one in which the components of the universe operated in concert with remarkable speed and sophistication. By the conclusion of this chapter, it was clear that cosmic dust was more than an incidental detail. It was a central architect of early galaxy evolution. Its presence demanded reevaluation of star formation timelines, chemical enrichment models, and even assumptions about the early universe's transparency. Webb had not merely glimpsed galaxies. It had unveiled the scaffolding that allowed them to exist, thrive, and evolve with unexpected rapidity. Dust, in this context, became a symbol of the universe's hidden complexity, a tangible marker of processes that accelerated cosmic history and defied conventional expectation. In sum, Webb's revelation of abundant early cosmic dust transformed the understanding of the infant universe. It highlighted the sophistication, efficiency, and dynamism of the cosmos, illustrating how matter, energy, and chemistry were interwoven into a network of accelerated evolution. Dust was no longer debris. It was a crucial actor, shaping the pace, structure, and destiny of galaxies. Through Webb, humanity glimpsed the universe's hidden artistry, a young cosmos already rich, complex, and astonishingly mature. Magnetic fields, invisible yet profoundly influential, emerged as another unexpected revelation from Webb's observations of the early universe. While their presence in nearby galaxies had been studied for decades, their role in shaping cosmic evolution in the first billion years after the Big Bang was largely theoretical. Webb's high-resolution imaging and spectroscopic data suggested that these primordial magnetic fields were already dynamically significant, guiding the formation of stars, regulating gas flows, and influencing the behavior of early galaxies in ways that defied conventional expectations. These fields were subtle architects, shaping the cosmos from behind the scenes, yet their fingerprints were evident in the structure, motion, and evolution of early galaxies. Evidence of magnetic influence came from the alignment and distribution of star-forming regions within galaxies. Some early galaxies exhibited coherent patterns of gas and dust flow, suggesting that magnetic forces helped channel material into dense knots where stars could form rapidly. This implied that magnetic fields were not weak background phenomena but active agents facilitating accelerated star formation. In combination with other observed anomalies, such as mature galaxies, supermassive black holes, and rapid chemical enrichment, these magnetic effects offered a tantalizing explanation for how the early universe could achieve such complexity in a fraction of the expected time. The impact of magnetism extended to galactic rotation and structure. Observations indicated that some young galaxies maintained surprisingly stable disks, even amid interactions and collisions with neighboring systems. Magnetic fields could provide additional support against gravitational collapse, helping preserve ordered rotation and structural coherence despite violent environmental conditions. This challenged prior assumptions that early galaxies would be highly turbulent and irregular, highlighting that magnetism may have played a stabilizing role in the rapid assembly of complex galactic architectures. Moreover, magnetic fields appeared to influence the behavior of supermassive black holes. The accretion of matter onto these gravitational giants is shaped not only by gravity but also by the magnetic fields threading the surrounding plasma. Webb's data suggested that early black holes were surrounded by magnetized environments that could regulate the inflow of gas, control jet formation, and impact energy output. The interplay between magnetism and black hole growth added another layer of complexity to the early universe, revealing a subtle yet powerful mechanism that accelerated evolution and shaped the cosmic landscape in ways previously unimagined. Theoretical implications were profound. If magnetic fields were strong and coherent enough in the early universe, they could have contributed to the accelerated formation of stars and galaxies, helping explain many of the anomalies Webb revealed. They might have interacted with turbulence, dark matter, and radiation to facilitate rapid collapse of gas clouds, efficient star formation, and even the distribution of heavy elements. In this sense, magnetism was not merely a supporting character but a crucial driver in the cosmic drama, orchestrating processes that led to the early maturity observed across multiple systems. Observationally, the influence of magnetism was subtle but discernible. Webb's infrared sensitivity allowed scientists to trace polarized light and map the orientation of dust and gas structures within galaxies. Patterns emerged that could only be explained by the guiding presence of magnetic fields, directing flows of material over thousands of light-years. These findings suggested that magnetism was already a coherent, large-scale feature of the cosmos, not a random or incidental property. It was shaping evolution in a universe still in its infancy, a hidden force quietly imposing order on a chaotic environment. The philosophical and emotional impact of these discoveries was significant. Magnetic fields are intangible, imperceptible to human senses, yet Webb revealed their decisive role in the shaping of reality on the grandest scales. Their presence challenged assumptions about simplicity in the early universe, emphasizing that even forces invisible to the eye can dictate structure, growth, and destiny. humanity was confronted with the idea that the universe's earliest architects were not only stars, black holes, and gravity, but also subtle, pervasive fields of magnetism weaving order into the cosmic fabric. The interplay of magnetism with other early universe phenomena underscored the interconnectedness of cosmic evolution. Collisions, chemical enrichment, star formation, black hole growth, and dust dynamics all appeared influenced by magnetic forces, creating feedback loops that accelerated development in multiple dimensions simultaneously. Webb's observations suggested a cosmos where energy, matter, and invisible forces were deeply intertwined, working in concert to produce complexity at speeds far beyond prior expectations. By the conclusion of this phase, it was clear that magnetic fields were essential to understanding the early universe. They provided an unseen scaffolding, guiding material flows, stabilizing structures, and influencing the pace of evolution in ways that helped reconcile some of the paradoxes Webb had revealed. Without accounting for magnetism, the rapid maturation of galaxies, the efficient formation of stars, and the orderly structures observed would remain inexplicable. In sum, Webb's insights into magnetic fields transformed humanity's understanding of cosmic forces. These invisible threads were not merely peripheral phenomena, they were central architects in the universe's early evolution, quietly shaping reality, accelerating processes, and orchestrating a cosmos far more sophisticated and mature than previously imagined. Through Webb, humanity glimpsed the hidden machinery of the universe, a force both subtle and mighty, threading its way through the earliest chapters of cosmic history. Dark energy, the mysterious force accelerating the expansion of the universe, had long been a theoretical cornerstone, but Webb's observations gave it a new, almost tangible presence in shaping the cosmos. While its effects were well studied in the relatively nearby universe, its role in the first billion years remained largely speculative. Yet Webb's deep-field images and precise measurements suggested that dark energy may have influenced the early universe far more actively than previously assumed, affecting galaxy formation, the distribution of matter, and even the apparent maturity of early cosmic structures. This revelation forced scientists to confront an unsettling possibility. The universe's expansion, driven by dark energy, may have been far from uniform, creating pockets where evolution proceeded at accelerated rates, allowing galaxies to form and mature far earlier than traditional models predicted. The implications were staggering. In regions where dark energy exerted slightly greater influence, gas could have been pushed into structures more rapidly, compressing matter in ways that catalyzed star formation and galactic assembly. Conversely, areas with slightly weaker effects might have evolved more slowly, leading to a patchwork universe where cosmic maturation occurred unevenly but efficiently. This uneven expansion could help explain the paradox of mature galaxies existing in epochs previously thought too brief for such development. The universe, once assumed to expand as a steady backdrop for evolution, was now a dynamic participant, shaping the pace and structure of early cosmic history. Observational evidence supporting dark energy's early influence came in subtle forms. The relative brightness, size, and distribution of distant galaxies hinted at differential expansion rates, while the clustering patterns suggested that certain regions experienced accelerated growth. Webb's unprecedented resolution allowed scientists to detect these nuances, revealing a universe where expansion and evolution were intertwined in complex ways. The data implied that dark energy was not merely a distant, abstract force but a cosmic architect, guiding the tempo of creation, influencing the flow of matter, and accelerating the development of structures in the earliest epochs. The theoretical ramifications extended deep into cosmology. If dark energy varied spatially or temporally in the early universe, it would challenge the long-held assumption of a constant cosmological constant. Models of galaxy formation, stellar evolution, and large-scale structure would require recalibration to account for a universe in which the rate of expansion could fluctuate subtly but meaningfully. Scientists began to explore scenarios in which dark energy interacted with dark matter or baryonic matter in unexpected ways, amplifying galactic growth or redistributing material to favor rapid structural evolution. These ideas, once speculative, became urgent areas of research as Webb's observations provided evidence that could no longer be ignored. The impact of dark energy on cosmic timelines was particularly profound. The paradox of mature galaxies, heavy chemical enrichment, and supermassive black holes could no longer be considered anomalies. Instead, they might be natural consequences of regions where dark energy accelerated evolution. By subtly altering the rate at which space itself expanded, dark energy could have created conditions conducive to rapid star formation, efficient black hole growth, and the early assembly of complex galaxies. In essence, it acted as an invisible conductor, orchestrating the symphony of creation at a pace that confounded human expectations. The interplay of dark energy with other cosmic forces added layers of complexity to the early universe. Magnetic fields, cosmic dust, and gravitational interactions all operated within the expanding spacetime framework shaped by dark energy. Together, these forces created feedback loops that accelerated evolution, guiding galaxies along paths of rapid maturation while leaving other regions comparatively underdeveloped. Webb's ability to detect subtle variations in galactic properties and distributions provided the first hints of these interactions, suggesting a universe in which acceleration, energy, and matter worked in concert to defy conventional chronology. Philosophically, the early influence of dark energy raised profound questions about determinism and the nature of time. Humanity had long assumed that cosmic evolution followed predictable, linear trajectories, governed by gravity and thermodynamics. Yet Webb's data suggested a universe capable of non-uniform evolution, where forces like dark energy could modulate growth and create pockets of accelerated development. The cosmos was no longer a passive arena unfolding according to fixed rules. It was a dynamic entity, actively shaping its own history, and in doing so, challenging humanity's understanding of causality, scale, and the very flow of time. Visually, the consequences of dark energy's early influence were subtle but dramatic. Galaxies that formed in regions of accelerated expansion appeared brighter, larger, and more organized than their surroundings, standing out like beacons in the vast cosmic tapestry. Webb's infrared imaging revealed these contrasts in exquisite detail, highlighting the uneven but efficient nature of early cosmic evolution. These differences underscored a universe that was heterogeneous, dynamic, and capable of producing complexity with breathtaking speed. By the end of this phase of Webb's revelations, dark energy emerged not as a distant abstraction but as a vital agent in the early universe. It helped accelerate star formation, guided galactic assembly, and shaped the large-scale structure of the cosmos in ways that had previously been unimagined. The mature galaxies, chemical richness, and rapid structural development observed by Webb could now be understood as natural consequences of a universe subtly but powerfully influenced by this invisible force. In sum, dark energy was not merely a background phenomenon but a driver of early cosmic evolution, accelerating development, shaping structure, and influencing the pace at which the universe matured. Webb had illuminated its subtle fingerprints, revealing a cosmos where unseen forces orchestrated reality, defying expectations, and pushing the boundaries of human understanding. The early universe was not a passive stage but a dynamic, accelerating entity, and dark energy was one of its most powerful and enigmatic actors. The cosmic web, the vast, intricate network of filaments and voids that connects galaxies across the universe, took on a new level of significance through Webb's observations. Previously, the large-scale structure of the universe was thought to emerge slowly, with galaxies gradually clustering under the influence of gravity over billions of years. Webb, however, revealed hints that the scaffolding of the cosmic web was already remarkably developed in the universe's infancy. Filaments of dark matter and gas stretched across intergalactic space, connecting galaxies in patterns that suggested accelerated structure formation and challenging the conventional narrative of gradual cosmic assembly. The universe, it seemed, was organizing itself with surprising sophistication from its very beginnings. The evidence for these early filaments came from the distribution of galaxies and gas observed in Webb's deep-field images. Galaxies appeared not as isolated entities but as nodes within interconnected networks, aligned along elongated structures spanning hundreds of thousands of light-years. These alignments implied the presence of underlying dark matter filaments acting as cosmic scaffolding, guiding the flow of baryonic matter and shaping the locations where galaxies could form. The contrast between dense clusters along these filaments and vast, Empty voids in between underscored the universe's ability to establish complex patterns almost immediately after the Big Bang. Gas dynamics along these filaments also revealed the mechanisms driving early cosmic evolution. Streams of gas funneled into nascent galaxies, feeding rapid star formation and contributing to the accelerated growth of supermassive black holes. Webb's spectroscopic observations indicated that these inflows were efficient and coherent, channeling matter along predetermined paths dictated by the underlying cosmic web. This process allowed galaxies to mature far faster than traditional models predicted, offering a potential explanation for the age paradox and the unexpected chemical richness observed in the early universe. The interplay between filaments and magnetic fields added another layer of complexity. Magnetic forces appeared to guide the movement of ionized gas along these structures, stabilizing inflows and shaping the formation of stellar nurseries. Dust and heavy elements, produced in the earliest stars, were also transported along these cosmic highways, distributing the building blocks of galaxies across vast distances. Webb's observations suggested that the early universe was not chaotic but organized, with multiple forces, gravity, magnetism, and radiation, working in concert to accelerate the evolution of cosmic structures. Collisions and mergers were amplified along these filaments as well. Galaxies forming at the intersections of filaments were more likely to encounter neighbors, triggering gravitational interactions that further accelerated star formation and galactic maturation. The cosmic web thus acted as both a scaffold and a catalyst, organizing matter while simultaneously fostering the energetic processes necessary for rapid evolution. Webb's imagery captured this interplay with breathtaking clarity, showing galaxies strung like luminous beads along invisible threads, some already interacting violently despite their young cosmic age. The existence of a structured cosmic web so early in the universe had profound theoretical implications. Standard models had predicted that filaments and voids would emerge gradually, as density fluctuations in the primordial matter grew over billions of years. Webb's observations suggested a more efficient mechanism, one in which dark matter and baryonic matter coalesced into intricate networks much sooner than expected. The early presence of these structures implied that forces shaping the universe, gravity, dark matter, dark energy, and possibly exotic physics, were operating with remarkable precision and speed, challenging assumptions about the timeline and mechanics of cosmic evolution. Philosophically, the early cosmic web reinforced the theme of order emerging from apparent chaos. Humanity tends to perceive the universe as gradually assembling its complexity, yet Webb revealed a cosmos that was pre-wired for structure, where galaxies, stars, and matter were distributed according to invisible, elegant patterns. The contrast between the observable chaos of individual galaxies and the large-scale order of the web highlighted the dual nature of the cosmos. Locally turbulent, globally coherent, and capable of achieving sophistication far earlier than the human mind could intuitively grasp. Visually, the cosmic web offered some of Webb's most striking imagery. Filaments glowing with nascent star formation connected clusters of galaxies, while intervening voids stretched across light years of emptiness. The interplay of light and shadow, dense clusters and vast voids, created a cinematic tapestry of contrast, emphasizing the universe's dynamic architecture. These observations conveyed both beauty and a sense of scale, reminding humanity of the immense structures that govern cosmic evolution and the invisible threads that link the universe together. By the conclusion of this chapter, it became clear that the early cosmic web was not incidental but foundational. It provided the structure, connectivity, and pathways necessary for accelerated galaxy formation, rapid star production, and early chemical enrichment. Webb had revealed that the universe was far more organized at its inception than previously imagined, with a network of filaments acting as both scaffolding and conduit for cosmic evolution. In sum, the cosmic web in the early universe was a revelation of hidden order, an intricate framework that facilitated rapid development, channeled matter and energy, and interconnected galaxies across immense distances. Webb's observations transformed our understanding of large-scale cosmic architecture, highlighting the interplay of forces that orchestrated the universe's early maturity. It was a universe of threads, flows, and connections, woven with astonishing speed and precision, revealing a cosmos that was already sophisticated, coherent, and breathtakingly complex. Galactic rotation has long served as a window into the invisible forces shaping the cosmos, revealing not only the mass distribution of stars and gas, but also the hidden influence of dark matter. Webb's observations of early galaxies dramatically challenged previous assumptions about how rotation develops over time. Conventional models suggested that young galaxies should be turbulent, irregular, and dominated by chaotic motion, with coherent rotation appearing only after billions of years of gradual assembly. Yet Webb's high-resolution imaging and spectroscopic measurements revealed surprisingly ordered rotational patterns in galaxies formed less than a billion years after the Big Bang. These early disks spun with a stability and coherence that defied expectations, hinting at underlying forces and mechanisms that accelerated galactic maturation far beyond what theory had predicted. The evidence came from Doppler-shifted spectral lines tracing the motion of gas and stars across galactic disks. In multiple early galaxies, Webb detected clear velocity gradients indicative of rotation, with stars and gas moving in coordinated orbits around dense cores. Some galaxies even exhibited spiral-like structures or elongated bars, features thought to require extended periods of dynamic settling. The contrast between these organized systems and the chaotic environments expected for the early universe was striking, suggesting that galaxies had mechanisms to stabilize rotation and maintain structural integrity despite their youth and the surrounding cosmic turbulence. Magnetic fields and dark matter halos likely played central roles in this accelerated rotational development. Magnetism could have provided additional support against gravitational collapse, channeling gas into coherent flows and helping to maintain disk stability. Meanwhile, dark matter, invisible yet dominant in mass, could have created the gravitational scaffolding necessary for early rotational order. Webb's observations implied that these forces were interacting in sophisticated ways, allowing young galaxies to form stable structures far earlier than previously considered possible. The interplay of visible and invisible forces painted a picture of a cosmos capable of rapid organization, where galaxies matured not through slow accumulation alone, but through coordinated dynamics guided by multiple factors. The rotational dynamics also offered insights into star formation and chemical enrichment. Stable rotation can regulate the inflow of gas toward galactic centers, influencing the rate at which stars are born and heavy elements are distributed. Webb's early galaxies displayed both rapid star formation and surprisingly uniform chemical profiles, consistent with a scenario in which rotation and associated forces orchestrated the internal evolution of these systems. Rather than a chaotic assembly, the young galaxies appeared to function as self-organizing systems, balancing gravitational collapse, stellar feedback, and magnetic influence in ways that produced accelerated maturation. Collisions and interactions with neighboring galaxies added complexity to these rotational patterns. Webb captured instances of early galactic mergers where disks were warped, stretched, or partially disrupted, yet many retained coherent rotational structures despite violent encounters. This resilience suggested that early galaxies were not fragile, but dynamically robust, capable of maintaining order even amid the chaotic processes that dominated the infant universe. The images conveyed a duality. The universe was both violent and orderly, destruction and creation intertwined, and rotational coherence provided a stabilizing thread through this turbulence. The theoretical ramifications were profound. If rotation could stabilize so quickly, models of angular momentum acquisition, mass distribution, and galactic evolution required substantial revision. Scientists began exploring scenarios in which early accretion flows, magnetic fields, and dark matter halos collectively accelerated the establishment of rotational order. Such mechanisms would allow galaxies to achieve maturity in a fraction of the time previously thought necessary, helping to explain Webb's observations of massive, chemically enriched, and structured systems at early epochs. Rotation was no longer merely a consequence of cosmic evolution. It was an active agent shaping the pace and trajectory of galactic development. The visual and emotional impact of these findings was equally striking. Infrared images revealed glowing disks of stars and gas spinning gracefully across vast distances, a cinematic display of order emerging from the primordial chaos. Observers could see the orchestration of matter on scales incomprehensible to the human mind, the invisible forces guiding galaxies into coherent motion. The contrast between the expected turbulence and the observed elegance highlighted the universe's capacity for early sophistication, instilling both awe and a sense of profound mystery. By the end of this chapter, it was clear that galactic rotation in the early universe was more than a simple kinematic property. It was a manifestation of underlying cosmic order. Webb had revealed that galaxies were capable of achieving dynamical stability and structural coherence far sooner than expected, guided by a combination of gravity, dark matter, magnetism, and internal feedback processes. These findings underscored the broader theme emerging from Webb's observations. The early universe was not a simple, chaotic environment but a rapidly maturing cosmos, capable of organizing matter and energy into complex, self-regulating systems. In sum, early galactic rotation was a revelation of cosmic sophistication, demonstrating that young galaxies could achieve stability, coherence, and dynamical order amidst the surrounding chaos. Webb's insights transformed the understanding of angular momentum acquisition, structural evolution, and the forces shaping the infant universe, offering a window into the mechanisms by which complexity, maturity, and organization emerged on unprecedented timescales. The early universe, it seemed, had already learned to spin with precision, elegance, and efficiency, defying expectation and expanding the boundaries of human understanding. The discovery of supermassive black holes in the early universe was among Webb's most profound and perplexing revelations. Long considered the ultimate products of cosmic evolution, these gravitational titans, millions or even billions of times the mass of the Sun, were thought to require vast spans of time to grow. Conventional models predicted that such enormous black holes could not form until galaxies had matured over billions of years. Yet Webb's observations revealed their presence in galaxies formed less than a billion years after the Big Bang. This forced a radical reassessment. The early universe was capable of producing and nurturing gravitational monsters at a pace that defied theoretical limits, challenging our understanding of both black hole formation and galactic evolution. The evidence came from the intense radiation emitted by matter as it spiraled into these black holes. Webb's infrared spectroscopic instruments detected energy signatures consistent with accretion onto massive cores, with luminosities that rivaled entire galaxies. These early supermassive black holes were not dormant. They were actively consuming matter, influencing their host galaxies, and shaping the surrounding interstellar medium. Their presence raised immediate questions. How could such colossal entities form so rapidly? Were there unknown processes accelerating their growth? Or did the early universe possess unique conditions that allowed black holes to reach gargantuan sizes in record time? One possibility was the direct collapse scenario, in which massive gas clouds could bypass the traditional stellar phase and collapse almost instantly into black holes of tens or hundreds of thousands of solar masses. This process could then seed the rapid growth of supermassive black holes observed by Webb. Another theory proposed accelerated accretion, where black holes consumed surrounding matter at rates approaching or even exceeding theoretical limits, fueled by dense, gas-rich environments and channeled inflows along cosmic filaments. Both hypotheses suggested that the early universe operated under extraordinary conditions, combining immense gravitational potential, abundant matter, and energetic feedback mechanisms to accelerate black hole evolution. The impact of these black holes on their host galaxies was equally dramatic. Their immense gravity could stabilize galactic cores, influence star formation, and regulate the distribution of gas and dust. The interplay between black holes, magnetic fields, and cosmic filaments may have created feedback loops, enhancing the efficiency of galaxy assembly and chemical enrichment. Some regions displayed intense radiation and outflows, sculpting surrounding matter while simultaneously triggering new bursts of star formation. A cosmic dance of destruction and creation. These black holes were not passive observers but active participants in shaping the early universe. The contrast between expectation and observation was striking. Theories had predicted that the early universe would be dominated by small, irregular protogalaxies, gradually coalescing and producing black holes over billions of years. Instead, Webb revealed massive, structured galaxies harboring mature black holes, already influencing their environments in profound ways. The paradox forced scientists to reconsider timelines, physics, and the efficiency of early cosmic processes. The universe, once thought to evolve slowly and predictably, appeared capable of extraordinary speed, producing complexity and power far beyond previous imagination. Observationally, the presence of these supermassive black holes offered unique opportunities. Spectroscopic data revealed not only the accretion activity, but also the chemical composition of the surrounding matter, showing evidence of heavy elements and dust already in place. The rapid enrichment of these environments suggested that stars had formed, evolved, and died in record time, feeding both the black holes and the chemical evolution of the galaxy. The universe was operating in overdrive, combining stellar, chemical, and gravitational processes in ways that defied conventional understanding. Philosophically, the early presence of supermassive black holes provoked a profound sense of awe and unease. These objects, capable of warping spacetime and emitting energies that outshine galaxies, existed when the universe was still in its infancy. Their existence implied that the cosmos was capable of extremes beyond human expectation, producing forces of unimaginable scale and influence almost immediately after creation. They served as a stark reminder of the universe's power, unpredictability, and capacity for accelerated evolution. Furthermore, the discovery of these black holes intertwined with Webb's broader revelations, including early galaxy maturity, rapid star formation, chemical enrichment, and magnetic fields. Supermassive black holes acted as both catalysts and regulators, influencing nearly every aspect of galactic development. Their presence helped explain some of the anomalies observed in early galaxies, providing a gravitational anchor for rotation, concentrating matter, and potentially accelerating star formation. Webb had illuminated not just the objects themselves, but the dynamic ecosystems they fostered. By the conclusion of this phase, it was clear that supermassive black holes were central players in the early cosmos. They challenged theoretical expectations, reshaped understanding of galaxy formation, and demonstrated that the universe was capable of producing extraordinary complexity in astonishingly short timescales. Webb had revealed a universe in which gravity and energy combined to forge titanic objects, orchestrating cosmic evolution at unprecedented speed and scale. In sum, the early supermassive black holes captured by Webb were both a puzzle and a revelation. They embodied the universe's capacity for accelerated growth, extreme phenomena, and complex interdependence. Far from passive remnants, these black holes actively shaped their galaxies, influenced chemical evolution, and exemplified the rapid, dynamic processes that define the young universe. Humanity had glimpsed the raw power and sophistication of the cosmos in its formative years, a universe already capable of producing its most formidable creations with breathtaking efficiency and scale. The question of the universe's age and timeline took on new urgency in light of Webb's observations. Conventional cosmology had long relied on a relatively straightforward sequence. The Big Bang occurred approximately 13.8 billion years ago, followed by a gradual process of galaxy formation, star birth, chemical enrichment, and large-scale structure development. Galaxies observed at high redshift were expected to be small, irregular, and primitive, reflecting the short amount of time available since the cosmos began. Yet Webb's deep-field imaging upended this assumption, revealing galaxies that were massive, chemically mature, and structurally sophisticated far earlier than any model had predicted. This forced scientists to confront a profound paradox. The universe appeared older, or at least more evolved, than its chronological age would allow. The implications for cosmic chronology were staggering. If galaxies could achieve such maturity in less than 1 billion years, then either our understanding of time-dependent processes in the universe was incomplete, or the early universe operated under previously unrecognized physical conditions. Star formation, chemical enrichment, and black hole growth all appeared to proceed at rates far exceeding theoretical limits. This rapid evolution suggested that the cosmos had mechanisms for accelerated development, capable of compressing billions of years' worth of complexity into the first few 100 million years. Webb had revealed a universe that was not just young in age but astonishingly efficient in its growth. Observational evidence compounded the mystery. Spectroscopic measurements showed high levels of heavy elements, implying multiple generations of stars had already lived and died. Galaxies displayed coherent structures, rotation, and even hints of spiral arms, features thought to require extensive periods of stability. Supermassive black holes, cosmic dust, and dense star clusters all pointed to a universe that had matured with unprecedented speed. The contrast between expectation and observation created a tension that reverberated across the fields of astronomy, cosmology, and physics. Humanity had assumed a universe governed by slow, predictable evolution. Webb suggested a cosmos capable of accelerated, almost impatient sophistication. Theoretical responses began to emerge. Some scientists proposed modifications to star formation models, suggesting that the first generations of stars might have been far more massive and efficient at producing heavy elements than previously believed. Others explored exotic physics, including variations in fundamental constants, unknown feedback mechanisms, or previously unconsidered interactions between dark matter, dark energy, and baryonic matter. Each scenario aimed to reconcile the observed maturity of early galaxies with the universe's known age, yet all underscored a profound truth. Webb had revealed a cosmos more dynamic, complex, and efficient than any model had anticipated. This accelerated timeline had implications for the formation of large-scale structures as well. The cosmic web, galaxy clusters, and filamentary structures all appeared in place earlier than expected, suggesting that gravity, magnetic fields, and cosmic flows operated with remarkable efficiency. Collisions, mergers, and inflows along filaments were not just local events but components of a rapidly evolving, interconnected network. The universe was organizing itself on both small and large scales, simultaneously building galaxies and the scaffolding that connected them. A process that, according to traditional models, should have required much more time. Philosophically, the implications were profound. Humanity had long measured the universe in linear, comprehensible increments, assuming a predictable sequence from simplicity to complexity. Webb's revelations challenged this perspective, suggesting a cosmos capable of rapid, almost instinctive sophistication. Time, as previously conceived in cosmology, might not fully capture the dynamism of early cosmic processes. The universe had matured at an astonishing pace, compressing complexity into epochs previously thought incapable of supporting such development. This realization inspired both awe and a humbling reconsideration of humanity's place in a universe operating on scales and speeds far beyond human intuition. Visually, the paradox was striking. Webb's images juxtaposed young galaxies that appeared mature and structured against a backdrop of the infant universe, a cosmos still filling with radiation, dark matter, and primordial gas. The contrast emphasized the universe's dual nature. Nascent in age yet advanced in development, chaotic yet ordered, young yet remarkably sophisticated. Each observation reinforced the theme of accelerated evolution, challenging both scientific expectations and human imagination. By the conclusion of this chapter, the age paradox had crystallized as one of the defining mysteries revealed by Webb. Galaxies, stars, black holes, and cosmic structures all hinted at a universe operating with astonishing speed, achieving levels of complexity that defied chronological constraints. The telescope had not merely looked back in time. It had illuminated a cosmos whose internal clock seemed to tick faster than previously understood, compressing billions of years of evolution into a fraction of the expected duration. In sum, the early universe as revealed by Webb forced a radical rethinking of cosmic timelines. The age paradox highlighted a universe both young and extraordinarily mature, capable of accelerated formation, rapid chemical evolution, and complex structural development. Humanity was confronted with a cosmos that defied expectation, operating on scales, speeds, and efficiencies far beyond conventional imagination. Webb had shown that the universe was not simply old or young in chronological terms. It was astonishingly, efficiently, and mysteriously alive from its very inception, challenging every assumption about time, growth, and cosmic evolution. The concept of cosmic anomalies had always existed on the periphery of astrophysics, intriguing theorists but often dismissed as statistical outliers or observational errors. Webb's observations, however, elevated these anomalies from curiosities to central pillars of early universe science. Across multiple deep-field surveys, the telescope revealed phenomena that contradicted long-standing models. Galaxies appearing too massive for their age, chemical compositions indicating multiple generations of stars, supermassive black holes already dominating galactic centers, and structures that seemed improbably coherent given the expected chaos of the early cosmos. These anomalies were not isolated. They formed a pattern, a chorus of contradictions suggesting that the infant universe was operating under principles and efficiencies far beyond human expectation. Each cosmic anomaly raised profound questions. How could galaxies grow so quickly without violating physical laws governing star formation and mass accumulation? How could supermassive black holes form in less than 1 billion years, and what mechanisms fueled their extraordinary growth? How could chemical enrichment occur at a pace that seemed to compress the life cycle of multiple stellar generations into mere hundreds of millions of years? Webb's data forced scientists to confront these questions head-on, pushing theoretical models to their limits and prompting the consideration of new physics or previously unappreciated processes that might accelerate cosmic evolution. The anomalies were not only quantitative but also qualitative. Webb revealed galaxies with morphologies and structures that seemed advanced, with disks, bars, and rotation already in place. Cosmic dust and heavy elements were distributed in patterns suggesting complex internal dynamics and efficient feedback mechanisms. Magnetic fields appeared to organize gas flows on galactic scales, while cosmic filaments funneled matter in ways that accelerated star formation. Taken together, these observations implied a universe capable of self-organization, efficiency, and sophisticated interplay of forces at a stage previously thought too early for such maturity. One of the most compelling aspects of these anomalies was their consistency across multiple independent observations. Different regions of the sky, diverse galaxies, and varying environments all displayed signs of accelerated evolution and unexpected complexity. This pattern suggested that the anomalies were not random but fundamental features of the early universe. Scientists began to explore frameworks in which the early cosmos operated under different conditions. Higher gas densities, more efficient star formation, or perhaps unknown interactions between dark matter, dark energy, and baryonic matter. Webb's revelations made it clear that these anomalies were signals, guiding researchers toward a new understanding of the processes that governed the infant universe. The emotional impact of these anomalies was profound, both for scientists and for humanity's broader understanding of the cosmos. Each contradiction challenged long-held assumptions, inspiring awe at the universe's ingenuity and humility in the face of nature's complexity. The anomalies created a narrative tension in the story of the cosmos, juxtaposing expectation with observation, theory with reality, and simplicity with sophistication. They highlighted the universe's ability to surprise, to operate beyond human models, and to achieve astonishing maturity under conditions previously thought prohibitive. The anomalies also fostered collaboration across disciplines. Astronomers, cosmologists, theoretical physicists, and computational modelers all grappled with the implications, seeking mechanisms to reconcile Webb's data with established physics. Simulations were adjusted, new hypotheses tested, and previously overlooked processes re-examined. In this sense, the anomalies became catalysts for scientific progress, pushing the boundaries of knowledge and driving the development of more nuanced, sophisticated models of cosmic evolution. Visually, the anomalies were striking. Webb's deep-field images juxtaposed expected primordial forms with galaxies that looked mature, chemically enriched, and structurally complex. Supermassive black holes shone brightly in galactic centers, dust clouds glowed with reprocessed starlight, and cosmic filaments channeled matter along coherent pathways. The imagery conveyed both beauty and mystery, highlighting contrasts between expectation and reality, chaos and order, youth and sophistication. Each image was a testament to the universe's ability to surprise, challenging observers to rethink the nature of cosmic evolution. By the conclusion of this chapter, it was clear that cosmic anomalies were more than curiosities. They were signposts, revealing fundamental truths about the early universe. Webb had not merely captured images. It had unveiled a cosmos operating on unexpected timescales, with processes and efficiencies that challenged the core of astrophysical theory. These anomalies underscored a central theme. The universe was far more capable, complex, and mature in its infancy than previously imagined, forcing humanity to reconsider what was possible in the first billion years after the Big Bang. In sum, Webb's cosmic anomalies were a revelation of the unexpected, a confrontation with the limits of human understanding. They highlighted the universe's accelerated evolution, structural sophistication, and dynamic complexity, challenging conventional wisdom at every turn. Humanity was confronted with a cosmos that did not simply follow predictable patterns but operated with ingenuity, efficiency, and subtlety, revealing a young universe that was astonishingly advanced, profoundly mysterious, and full of lessons yet to be deciphered.